So now, I guess we'll get started with the talk. Let me introduce Yi Sun from Axiom. He's a co-founder. He's the founder of Axiom, and just briefly on what Axiom does. Um, they are building a ZK coprocessor, and they're essentially trying to build a verifiable data, have developer access verifiable data, and be able to perform arbitrarily complex compute on top of it as well. So, Isun, do you want to take it off from here?
Awesome. Yeah, thanks for the introduction, Yuki, and thanks for organizing this wonderful event. So today I wanted to talk a lot about a slightly off the beaten track topic, which is what ZK can do for developer experience for on-chain applications, and our perspective on that at Axiom. So to kick off, wanted to talk about some of the motivation we had for even starting Axiom, which is when we looked at smart contract applications, we found that they're really data starved. What that means is that smart contracts really can access a limited fraction of all data that's even on-chain today. So if you look at a listing page on OpenSea and you try to identify which pieces of on-chain data are actually accessible to smart contracts from that page, you'll quickly realize that it's actually just the present owner. So for this Pudgy Penguin, the fact that it's owned by Zac Efron is usable on-chain, but the rich transaction history and previous prices are not, although they are trustlessly available to any observer of the chain. And the reason for this is to preserve the decentralization of the chain and allow full nodes to validate transactions easily. So this isn't just a failing of Ethereum, but more of a fundamental trade-off that any blockchain must make. So as a consequence, developers have a pretty painful trade-off to make today. If they want to access more data trustlessly, then what they need to do is pay more and store the data in state. So this has two problems. The first is that it obviously costs more. What that means is that every user has a bit of a negative externality. But actually, more concerningly, it introduces a lot of complexity on the part of the developer. You have to actually couple your business critical systems, for example, maybe your core matching algorithm on chain, with things that are less critical. For example, how you maybe reward users or your loyalty system. And this violates some basic principles of software modularity and also introduces some security risk. Now, your other choice as a developer is basically to reduce the security of your on-chain application. You can use a trusted oracle to introduce data to your application, which will definitely work, but will introduce additional trust assumptions for your users. And those trust assumptions might not scale as you compose your application into others. And so as a consequence, today developers basically have to choose between increased cost and complexity or reduced security. And so we asked ourselves how we can simplify the design of smart contract applications so that developers don't have to think about all future uses of their on-chain data when writing their initial applications. And our answer to this is that we need to dramatically scale data access for smart contracts. So why do we even think this is possible? Well, blockchains actually offer a different way to access data outside of the consensus that's provided by the EVM. So blockchains all have a property that the current block commits to the entire history of the chain. So for Ethereum, this means that the current block commits to all past blocks, and each block commits to the state, transactions, and receipts inside that block. By decommitting all these commitments, we can access the chain history using cryptography instead of consensus. Now, how does this work? Well, to actually show that you possess a valid transaction from a block that's 1 million blocks ago, what you have to do is demonstrate first that the block header of that block is valid. To do that, you have to verify a Keccak chain of block headers from that previous block header to the current block. Namely, you need to show that the past block has a header whose hash appears in the next block, and that block has a header whose hash appears in the next block, and so on. After you've proven that the past block header is valid, you actually have to give a Merkle-Patricia-Trie proof for the inclusion of your transaction in the previous transaction trie. And so as you might notice, this involves a chain of hashes of 1 million block headers, which is prohibitively expensive in the EVM. So instead, by using the power of ZK, what we do at Axiom is to essentially check this proof in ZK. So we take this large computation and make a ZK snark that the Merkle-Patricia-Trie proof was valid, and also that we possess a valid chain of block headers from a past block all the way to the current block. Because ZK allows us to compress the verification of this to a succinct computation, this allows us to do this large-scale computation in a way which is verifiable on-chain. Furthermore, it allows us to compose such computations for downstream usage. So we packaged this up at Axiom into something we're calling a ZK coprocessor for Ethereum. What that means is that smart contracts can query into Axiom to perform two operations. First, to read historic on-chain data, and second, perform verified compute on that data. Once we come to a result, we post it on-chain and verify a zero-knowledge proof that it's valid. After that, a downstream application can use that result with the same security guarantee as data that it reads from Ethereum itself. And our philosophy at Axiom is that we should always have security that's cryptographically equivalent to Ethereum without imposing any additional trust assumptions on our users. So what's the advantage of this type of design? So first, by reading from historic on-chain data, we allow Axiom to actually trustlessly interoperate with existing applications. What that means is that when you're designing a smart contract application, you actually don't need to think about what are the later usages of the data that you're caching in your application. So today, applications have to really think carefully about what aspects and side effects of their transactions they might need to reference later. If you don't store that in state, then it's sort of gone forever for the on-chain usage. With Axiom, you can exactly read that data and later make use of it, even if you didn't anticipate that usage at the time of deployment. After reading that historic data, we allow you to compute without being limited by the blockchain VM. Because we're verifying compute in ZK, this doesn't need to respect gas limits or the specific computations that are cheap in the EVM. So let me just give a rundown of how ZK coprocessing with Axiom works today and how we think it's actually improving the developer experience. So what we're offering is trustless reads to historic block headers, accounts, and contract storage variables on mainnet today, and transactions and receipts on testnet. And on top of that, we're allowing compute via custom ZK circuits. So I'll go through a few examples of how this might change your actual experience as a developer. So today, if you're only using Solidity, then to track the user's participation in governance, what you have to do is that on every single time a user votes, you have to actually track the cumulative number of times they participated in governance. Then later, if you want to reward users for the number of times they voted, you have to read that cumulative participation count from your local contract storage. The disadvantage of this is that you have to pay additional gas to actually update the participation count every single time your users vote on chain. This obviously increases costs to voting, and this can decrease voter participation in on-chain governance, which is already challenged due to the gas cost. By using ZK to read the history, we can change the design of this application. Instead of actually tracking the cumulative vote counts, all we have to do is trustlessly read the historic vote events for each user. Then, when a user wants to claim a reward for historic voting, all they have to do is read these events and compute the number of times they actually voted. After proving that to a smart contract, the contract can reward the user or give them special rights, depending on whatever the developer wants to do after the fact. In a second scenario, suppose you wanted to make Uniswap fees dependent on the volume that a user has traded in the last week. Today, to make that possible, you'd have to track for each user their cumulative volume on every trade. What that means is that every Uniswap pool would have to maintain a list for every user of the total volume and keep that updated every single time it makes a swap. What that means is that every swap is going to be more expensive for each user, essentially because the volume updates might be comparably expensive to the actual swapping itself. Obviously, that's unacceptable. But as a result, so if you were to make such a system, you'd be able to read the cumulative user volume and then compute fees dynamically. If we use ZK to implement such a system, we can invert the architecture. This would allow us to make no changes to the current Uniswap system, but instead trustlessly read historic trade events for each user. By processing those events, we can compute the total volume that a user has traded and add up that volume to determine the fee rebate that a user is entitled to. Once every user does this, they can submit a proof of their historic activity to a contract and trustlessly obtain whatever volume rebate that the system decides they are entitled to. So as you can see in this case, typically in smart contracts today, you actually have to bake into your core application logic of swapping the idea that you might care about volumes in the future. But by using ZK, we can remove the need for developers to actually do that. Instead, later on, once we decide to develop this volume-based fee rebate system, we can go back and retrofit it onto our existing application without making security-critical code changes to the core swapping logic. And just to give one more example that I'm pretty excited about, if you look at airdrops today, if you want to make airdrops fully trustless, namely not dependent on the actions of a centralized team or token distributor, what you actually need to do is tally all potentially useful user actions on chain. What that means is that when you deploy your smart contract, you need to know the space of actions that you might later want to reward or incentivize, and track for each user the extent to which that user actually took those actions. That might be pretty expensive, and it might also be hard as a developer for you to anticipate. Typically, when you're shipping the first versions of your application, you're more concerned with your core business logic and with just making sure everything is secure, and probably less thinking about the space of future incentivization you might want to enable. As a consequence, if you later want to compute rewards on-chain, the only things you're able to use are the information that's being tracked in the state of your contract. You see this today in the form that most rewards are simply done by staking some type of fungible ERC20 token. Often that doesn't actually match the incentives that application developers want to set, but it's frankly the only information that they have available to make these choices. Using ZK, we offer smart contract developers much more flexibility. Instead of specifying the space of data that they want to take into account, the developers can trustlessly read all historic user activity on their application. And after the fact, when they want to design an incentive or rewards program, they can simply compute rewards based on arbitrary custom criteria over the entire history of activity in their application. So we think this is a much more flexible approach and also enables developers to have a much more modular design to their application architecture. So let me close by just talking about where we think ZK coprocessing is going. So we're already offering trustless reads to all on-chain historic data. And we think the next step is to offer view function simulation by running a ZK EVM proof on top of the storage reads that we're already providing. Together, that will create a ZK archive node or indexer, depending on your terminology. On top of the data returned by this system, we think it makes sense to offer users arbitrary computation via ZK native VM. So we'll have more to say in this direction in the next few months, so watch out for our upcoming releases. So that's all I have for today. We're Axiom. We have a ZK coprocessor for Ethereum live on mainnet, and you can check out our docs and demos. I wanted to mention at the end that we're running a new program called the Axiom ZK Intensive, which is targeted at helping smart contract developers learn to develop ZK-enabled applications. So applications just opened for this program and are closing September 18th, and you can apply at the link below. Thanks for the time, and happy to take any questions.
Thank you very much. So I guess to kind of just kick it off and on the questions, one thing I was kind of curious was like for the arbitrary compute, right now you have specific circuits for maybe specific functions, maybe some hashing functions, some arithmetic operations and whatnot. What is the sort of like the thinking behind the shifting towards more like a ZK native VM as an approach to enable those compute instead of like, let's say what you're doing right now is just like building more specific circuit. What is the consideration there?
Yeah, we're always actually driven by the developer experience. I actually don't necessarily think that a ZK native VM is always easier for developers, but we do think in some cases it's going to be a little easier. So our point of view is that, actually we think about what are the developer frictions in deploying actual functions that they might want to use on chain. Today, I actually think it's probably not a VM. It's more just having all the primitives that they're used to being implemented in ZK, and also being able to easily express those primitives.
I see. So in that case, you could see a scenario where with enough specialized circuits that perhaps the ZK native VM wouldn't be as useful in that kind of scenario.
Yeah, my feeling is the main criterion is actually not necessarily whether you have a VM or not, but more how fast you can implement, and also how fast you can have your circuit audited and be really sure that what's being proven on chain actually matches the application logic you're interested in. So VM definitely helps for that, but I think having a very clear sort of circuit language and framework can also achieve very similar goal.
Mm-hmm. Gotcha. And also one more thing that I also wanted to ask about was the ZK EVM proof that you mentioned towards the I guess the second to last slides. Could you elaborate a little bit more on like what do you exactly mean by ZK EVM proofs?
Yeah. So right now, when you use ZK to read data from your application, you kind of are introspecting about your application state. But what you have to do is operate on the raw data underlying your application. So in some cases, this is very straightforward. If you have a mapping, for example, for balances, that's a mapping from addresses to numerical values. And that can be read very directly. But actually, for some contracts in the wild, the balance computation or other computations are implemented via view functions that do some pretty simple computation on top of the storage access. And we think the ultimate developer experience will be to exactly run the Solidity or EVM computation that's deployed on chain on a historic state. So that, unfortunately, is much more complex. It requires you to actually simulate the full ZK EVM on a historic state.
Gotcha. And then I guess one question that I saw was asking, will this benefit stateless Ethereum? So I think the question is probably more so asking about like whether this is applied to like a stateless chains, or if it is like just specifically like Ethereum itself, or if you have any like plan around like working outside of Ethereum, or if it's just like within constrained within Ethereum frameworks.
Yeah, we actually spoke a bit with the Ethereum's stateless client team. And I think what we're doing is somehow parallel to the goal of statelessness, but some of the constraints are a little different. So you can view the data we provide as we're using ZK to give a cryptographic proof of the validity of that data. And in a stateless client, you would use probably not ZK to give a proof of every data access. I think the differences in having a stateless client versus what we're doing in Axiom is the stateless client would probably access a lot less data per block, but the latency requirements are much harsher. So in a stateless client, you have to be able to generate the witnesses in under one block. So you actually have a time budget of maybe seconds. Whereas at Axiom, we're enabling contracts to do much larger scale computations. And okay, does not take just seconds.
Gotcha. And then also, I guess one thing that I was kind of curious, because I think when I go through the decks, you also talk about like arbitrarily complex compute on top of verifiable data. Now, obviously, like that is a pretty broad statement, but at the same time, I believe that's also what it's intended for. But when I was thinking about like arbitrarily large compute, like what's the sort of the bound are we looking at? Like, and when we say like arbitrarily large, are we constrained by, let's say, the provers, the amount of provers that we have to support this kind of compute, or what is the constraints here that we're talking about that sort of like sets the bound for those kind of like arbitrarily large compute?
Yeah, generally we find actually the bound is just how much latency people are willing to tolerate. Obviously, if you're doing more compute, proving its validity will take longer. I actually think that typically the number of provers isn't necessarily a bottleneck, just because the function of proving isn't fully parallel. So you can definitely put some good number of provers to use, but before you hit your parallelism bound, you're probably going to hit your latency bound.
Gotcha.
But there's not really a conceptual bottleneck. And as we expect proof systems to keep getting faster, we think one of the main advantages of this type of architecture is that the compute isn't going to be gas limited. Like fundamentally, if you run compute on a rollup or any blockchain VM, you're limited by things like the sequencer and DA and this type of thing. Whereas in this sort of architecture, those aren't really factors because you're not operating in this shared compute context.
Gotcha. And then one more thing that I wanted to also discuss briefly was about the, I guess, as you mentioned, like a lot of the latency aspect. As you have said, like latency is a major concerns for users who are using Axiom, and essentially kind of trying to see like what kind of latency is acceptable for certain applications, and what kind of latency may not be the case, because I presume that some latency, some application might be more latency sensitive, while others maybe not so much. So I guess in that spectrum, like, do you foresee that Axioms to be initially catering for more like let's say latency sensitive ones, less latency sensitive ones, and how do you think that the latency game will kind of change over time?
Yeah, in general, our feeling is that as proof systems get better, latencies will go down across the board. I think that's one important distinction is that any sort of ZK-based data access or computation will always be asynchronous. So, the advantage you get from running something on-chain is that you really get access to synchronous changes in the state in the previous transaction. And that's something that no ZK-based system will be able to do, simply because you have to generate a proof relative to some chain state. And obviously, you don't know the chain state of an included transaction when you're submitting your transaction. Now, in terms of applications today, we actually found that things aren't necessarily so latency sensitive. And I think the reason for that is that if you think about non-blockchain computation, the main synchronous latency sensitive computations which exist in the world are actually in financial exchanges, like at NASDAQ or CME. Whereas if you think about almost all other computation, it's actually asynchronous. Like if you hit a web server in the microservice model, it's going to make a ton of async calls to other services and sort of react on callbacks to that. And we think that Axiom is fundamentally building that sort of system, but on-chain. Now, of course, users don't want to wait, let's say, an hour for results. And so we're tackling more use cases where the user has already accomplished something and they're getting a reward or requesting some sort of message that already takes a significant amount of time in alternatives as well.
Gotcha. That makes sense. I guess I think another aspect that I wanted to also touch upon was that the proof scheme. So I think today you might have not discussed too much about a lot of the proof scheme aspects, but I think it could be would love for you to share a little bit more about what kind of proof scheme that you are using right now, that you will be using in the future, or perhaps different ones or the same ones or whatnot. If you could elaborate on that as well.
Yeah, so today we're using Halo 2 with a KZG backend. So that's the general Plonkish arithmetization on the front end and KZG commitments on the back end for the polynomial commitment scheme. Yeah, so we're looking into a variety of more modern proof systems, including things like folding, large lookup schemes like CQ or Lasso, and also Fry with small fields. So hope to have more to share about that in the next few months.
Gotcha. Looking forward to that as well. So I guess on my end, that's it on the questions and the stuff. But again, thank you, E, for coming to the talk and sharing about the Axiom. And at the same time, for all the attendees here, please feel free to follow E on Twitter and also check Axiom's